All right, so going to talk about completing the cube again. I don't know, part two, part three, part four, don't know what to call it. But one of our last discussions of the semester, and time to tie a little bow around a lot of the things we've been working with. Now, I think that you should be prepared for your future levels of study. And part of that is to begin thinking about some of the more challenging concepts that you'll face. Because oftentimes math takes time to understand. Curiosity, patience, willingness to explore, all of those things are qualities that you should take into your studies. So I'm just going to present something to get the conversation started. And these concepts are built on Algebra 1 principles, but they take a little time to sort out in the brain. All right, so let's start with some user-friendly pictures and calculations. So I think this is a user-friendly calculation for looking at the numerical and graphical and geometric perspectives of a cubic. All right, so what's the shape? So I'll be asking some questions and you feel free to stop the video and think as long as you want, but what's the shape? And then I'm just going to continue with presenting. So x cubed plus 6x squared. I think you're looking at a box where two of the sides are equal and the third side is x plus 6. There, good enough box. If you were to graph it, you probably, textbook, if you've been doing some work out of a textbook, would have you factor. And I hope you can see the three dimensions. X squared times x plus 6. And the graph looks something like this. Oops, wait a minute, I botched that. And I don't have an eraser. Oh, go figure. All these videos, and I always have to walk over here to get an eraser. So much for that. So much for that. Well, actually, let's talk about it a little bit more. We've been studying when is this greater than 0, right? And I've been asking you to graph, so I hope you can see that at -6, you get a sign change, and at x squared, you don't. Okay, so that's what your graph looks like, something like that. And there appears to be a change of shape right around here. Concave down, concave up, which I'll talk about in more detail later. All right, so we got a graphical perspective, we got a geometric perspective. All right, so let's get the magic box out. Not yet for the magic box, but completing the cube is the process by which we can put cubics into graphing form. And cubic in graphing form with user-friendly numbers is about a 20-second process for finding local maxes and mins if they exist, point of inflection, rate of change at point of inflection, so on and so forth. So you can really get a good look at cubic with just a couple of memorizations of, how do you get the roots of the quadratic? Not the easiest method. Quadratic formula is not the easiest method, but everybody makes you memorize minus b plus or minus square root of b squared minus 4ac over 2a. It's a formula that helps you get some quick information. Pretty cumbersome. As I say, in most situations, you can handle it much more quickly and easily with other methods. So what's our frame of reference for completing the cube? Well, it's completing the square. So if you had x times x plus 6, then you go over here and you even off the sides and you say x plus 3 times x plus 3. I never leave enough space here. X plus 3. And if you square that, you get x squared plus 6x, but you also get 9. And so if you make the adjustment minus 9, now they're equal. And the beauty of this is you can use the square root now because you got a square. Can't use a square root on this. It's not a square. So that's our frame of reference. All right, so what did we do? We evened off the sides. Well, we got a picture here. All right, I guess I can move to where I've done it. So this video can keep moving along and you stop and think about any of this stuff for however long you want. But this is what I got to work with. That's my putty. So I'm going to even it off by breaking up into 3 parts, 2 by 2 by 2. All right, and if I multiply that out, I get x plus 2 cubed minus 12x minus 8. Because x plus 2 times x plus 2 times x plus 2, there's the squaring of the binomial, gives me this. It gives me that. And that's what this is right here. Those are equal. That gives me this. And if I want to get back, I got to make an adjustment. I got to get rid of what wasn't over here to begin with. Right? And so that launches us into a kind of a geometric study as well as a interplay of these changes, because that's not going to change right now. I'm going to change it in a minute to put this in graphing form. But I can kind of see an interplay of a cubic graph and a linear graph. And how do these things change locally? That's what we're going to be talking about here. All right, so this is almost in graphing form. This graphing form is based on the number -2, whereas this is kind of based on the number 0. We see change from 0 there more easily. We can see change from -2 volumes changing more easily from that perspective. All right, but going back to the graph, all right, point of inflection, it does seem as if this is 1/3 of the way to -6, -2. 1/3 of the way. And remember, we took that number and divided by 3. There's no accident here that this is happening. All right. So let's talk about, in general, a quick way of finding that x value. So if A is, I'm just assuming A is positive here. It doesn't really matter. But you can always factor x squared out of the first 2 terms, and you'll get this. And so where's our putty? Well, our putty's minus B over A. Right? Remember, a little while ago, we had x plus 6, and we used -6 as our reference. And now that makes it 0. So what makes it 0 for ax plus b? Minus b over a. The a's cancel, the b's cancel. So that's my putty. And if I take and divide it by 3, then I got the x value of the point of inflection very, very easily. Okay. A little later in the video, I'm going to do it with calculus. We're going to get to doing a little bit of introductory calculus because it's all based on Algebra 1 principles. So I think you're capable of following. And if you hear it enough, hopefully it makes some sense. Oh, just for the record, that's a double root. We call that a double root because I really have x times x times x, what was it, plus 6? Right? So 0, 0, -6, those are our 3 roots, and these are a double root. So there's 3 answers to 3 real numbers here that work. One of them just gets doubled up. So if a is greater than 0, we have a cubic that looks like that when a is bigger than 0 and m is greater than 0. I should have put that there. Okay. If a is greater than 0, then we got a n behavior going to infinity, n behavior going to negative infinity, and a slope of 0. Flat. Or we could have a slope that's negative at the point of inflection, but if a is greater than 0, then we're still going to negative infinity. So there's, for a greater than 0, there's 3 types of graph that might come your way. And everything is determined by whether or not we're going up or down at the point of inflection or staying at 0. Well, what makes that happen? What makes that happen? Why the point of inflection there? Well, you got to go back to geometry. You got a -2 times -2 times -2, which I've written in the table as -8. -1 times -1 times -1, -1. 0, 0, 1, 1, 2, 8. But if you look at the changes from -8 to -1, then you're going up at 7 to 1. And at -1, you're going up at 1 to 1. And at 0, you're flat. You're absolutely flat. So maybe I should make that look like it's going up a little bit more to meet it. And then we start again. So this is going up at 7, up at 1. Then we start going up at 1 again and up at 7 again. Well, these slopes are positive, but decreasing. These slopes are positive, but increasing. And that's what gives us that concave down, concave up shape. And why is it flat there? Well, I know one thing. There's no volume. And if there's no volume and I change each dimension Can I show where I changed each dimension? Did I draw that somewhere? I'll draw it now. If I increase this dimension, and I increase the height, and I increase the width, then I'm maintaining the shape. It's still a perfect cube, but I'm getting a change in volume. And so if I hold each of these changes to be a standard, let's use 0.001. And I come over to the table here. Now assume that at 0, 0 cubed is 0. But at 0.001, 3 decimal places cubed is 9 decimal places. I get 1, 2, 3, and then another 1, 2. So I'm adding up 1, 2, 3, 4, 5, 6, 7, 8, 9. And it's the first 3 decimal places divided by these 3 decimal places that I think gives us a good approximation for change. And I don't think that fits into 0 at all. I think my slope at the point of inflection appears to be 0. Things aren't changing much. But if I went to 1 and I did 1.001, well, now I'm going to show you the first 3 digits of change. And each one of these has 9 zeros. So add 0.0000000 to whatever change, 3 decimal places we get for change. And the 3 decimal places here are 0.002. The 3 decimal places for 2 are 0.012. The 3 decimal places for 3 are 0.027. And the 3 decimal places for 4 are 0.048. That's how things are changing. Now, let's just give you the magic box now. Let's say that this is a 2 by 2 by 2, a 2 by 2 by 2. If I make it a 2.001 by 2.001 by 2.001, I've increased the volume of the box. And it's like a sleeve, it's like a layer. Okay, it's like a layer. Boom. What's the formula for this? See if you can come up with the formula that measures the change at any instant of the magic box, how the volume changes. You ponder that. I'm just going to keep going. Well, if you correctly identified it, then it sure looks like it's connected to, and this is 0.000, it sure looks like it's connected to this formula. What's 1 squared? 1 times 3, a mistake on my part. Big time mistake. Excuse me. Pretty hard to see a pattern when the old guy gives you a number that's not right. My apologies. Okay, so all that pondering. I could say it was an April Fool's joke or something, but it wasn't. It was just carelessness on my part. But I'm not going to start this all over again. So if we square that, we get 4 times 3 is 12. If we square that, we get 9 times 3 is 27. If we square that, we get 16 times 3 is 48. And I hope you can see that diagrammed here or depicted here with the magic box layer. I think you're looking at 1 squared. 2 times 2, 4. 2 times 2, 4. 2 times 2, 4. 3 fours make 12. Now, where's the 0.001? Because this has volume. Where's the other dimension? I can see the width. I can see the height. Where's the other dimension? Well, I don't want to say height. I got width and length. So where's the height? Well, it doesn't matter. It could be width. It's the thickness of the box. I'm stumbling over the words here. It's the thickness. The thickness of the box I'm calling 0.001. If I want more accuracy, then I make a 0.001 thickness. And I can build in more accuracy. And that's what limits are all about. All right. The smaller the change, the more accurate the calculation. For what? y2 minus y1 over x2 minus x1. We're still talking algebra 1. Early calculus concept is really all based on these very simple foundational principles that you're studying now. So I think you should talk about what happens in a little more complex situation. Well, that's what we're looking at, right? And it's a layering process that we're actually just studying at the moment. All right, so let's keep building the concepts. Let's take Rene for another cart run. Okay, and let me move this desk. I should have prepared all this stuff. I should have done this long before starting this video. Let's hope this fits inside here nicely. Come on, Renee. There we go. Yeah, this is fine. All right, so let's pick up the conversation again. So I've made a new situation, but we have discussed this for the cubic. Let's discuss it for the square. Same thing. If this was 0, but we're changing, then this is 1, and then we're changing. It turns out the change, if I just increase, now I'm just looking at one square area. How does that change when these two dimensions change by 0.001? 0.001. Well, it turns out it's a layering like that. I can't show 0.01. Pretty hard to show that. All right, but it's that layering. I've added new area, and this new area would have 6 decimal places, 0.1, 2, 3, 4, 5, 6, because I'm going to be squaring 3 decimal places. And this one, let me make sure I don't make a careless error again, is going to be 0.000001. Okay, so the first 3 decimal places is what we're after. Okay, and so the first 3 decimal places here will be 0.002. Next one will be 0.004. And the next one would be 0.006. And the last one would be 0.008. So what I did is I did 4.001 squared minus 4 squared over 4.001 minus 4. That's my input. Okay, and this is the change I would get, along with 0.0000012345 And remember, I could push these things out so many zeros, 4, 3, 4, 5, 6, 7. That means I can do 7 here. 1, 2, 3, 4, 5, 6, 7 with another 1, 2, 3, 4, 5, 6, 7. That's the error. 0.0000000001. And that's really all about the cusp. Otherwise, what you had was that times 2, and 0.001 bump squared. There's your 6 decimal places that we're now extending out even further. Okay, but I guess I'm doing this one here. 0.002, 0.002. Okay, there's your 0.004 with that. But I can push that error rate right out the window. So here's a new one. And this is doing, without calculus, putting this in graphing form. We've established minus b over 3a is the x value at which this turns. We put in positive 6 divided by a is 1. I'll put that there. 3 times 1 gets us 2. And if we put 2 in, we get 8. We get minus 24. There's that 3-to-1 ratio with opposites, right? In the quadratic, we've done enough of those to see that it's 2-to-1. So we know we got the right number. If this was positive 24, you got a sign change error. So now, you put this together, you get minus 31, which means I now know I can complete the cube. I can write, and I changed this to a minus. It was a plus before, but now I'm using minus. X minus 2 cubed. And I know that there's going to be a linear component, x minus 2. And I know if I drop in a positive 2, I get minus 31. And I hope I didn't make any careless errors. So that turns out to be the general framework. We know a is 1. We don't have to put it there, but I will put that there. And now a simple formula will tell me the rate of change at that instant. And I got this formula long before I taught calculus. So might have been hit or miss. I don't remember. I thought that work is lost. So, and I don't feel like regenerating it. So somebody else can. Minus 10, minus 12, minus 22. Okay, so I now know that at 2, I'm at negative 31. I'm going down at 22-to-1, which means I have one of these graphs, and I keep doing that. I keep putting this in the way. All right, and so I've got, that was what? 2 comma negative 31. There we go. And I now can look at this, and I have a frame of reference, just like I did with completing the square. My frame of reference is 2. And I've gone backwards to the left, and I know I got to offset negative 22 with a rate of change coming from the cubic term of positive 22. And it's over 3a, because I've still got that three-dimensional process working its way through these. So that's 3. So that's that x value, and that's not done with calc. It's nice to know what the y-intercept is and the rate of change there. I know I'm over here. I'm going down at 10 to 1, and a 0 gets me 5. All right, I don't know what this is going to get me. I got, it's not friendly, but it's the value of the local max. All right, and I haven't proved why, but that's coming in future studies. Now, let's do it with calculus. With calculus, we've kind of established a few things. We've established the rate of change of the cubic. I don't know if I stated it in the video. I don't know if I stated it in the video, but it was 3x squared. I better go back there because my short-term memory is really disappearing. And where was it? Oh, yeah. So 1 squared 1 times 3 is 3. 2 squared 4 times 3 is 12. 3 squared 9 times 3, 27. I think I did that. But so we've established that x cubed changes by 3x squared. That's the layering process. And then we have that here. And x squared changes by 2 times x, and I'm multiplying that by -6, so that's going to go down to 12. And this is always changing at 10 to 1. I don't care if you make a big leap or a small 0.001. It's changing it, going down at a 10 to 1 rate. Well, that gives me a quadratic. That gives me slope at any instant of this graph. So over here, I can look at any instant, and I have a slope. I've got a couple. I've got -22 when x is 2. So let's do f of 2. And I put this in graphing form. Okay, I completed the square. I put a 0 in. I know a 0 gets me -10. So when I put a 0 in here, I got +12. I don't want +12. I get rid of it. I want -10. So now we can see the -22. Right? 2 gets us -4. What a coincidence. That's the same thing we got over there without looking at the slope formula. We looked at a different slope formula. Interesting. Yeah, and I just mentioned that you're going down at 10 to 1 at the y-intercept. Wow. Oh, well, let's put 0 in here. See what we get. We get 12 minus 22. Oh, what a coincidence. -10. Oh, so I actually know the y-intercept and the rate of change at that instant. That's a nice frame of reference. And it sure looks like this number should be, if that's 0, then this has to be smaller than 0. What's 22 divided by 3? 7? A little more than 7? Yeah, a little more than the square root of 7. And I know the square root of 4 is 2. So 2 minus 2 gets me 0. 2 minus something a little bit more than that. That should kick us. Okay, seems like those numbers are situated properly. All right. And then I decided that, well, let's take the rate of change of the rate of change. Rate of change of the rate of change. Sounds like acceleration or deceleration to me. So 3x squared, I guess I have a process here. 2 times 3 is 6, because this is supposed to be 3 times 2x. Well, that drops down 1, so I can see it drops down 1, and I'm multiplying. Gee, seems like it's pretty easy to get the slope of 3x squared, and we'll call it f tick mark x because it's tick season. You got to watch out for ticks. All right, and this is going to represent the rate of change of that. And so I've got a leapfrog here. That's 6x, -12. I don't think that's changing. If you see that number change, definitely write to me. Okay. I wonder when that's equal to 0. Oh, when x is 2. Another coincidence. Oh, another coincidence. Yeah. Yeah. Point of inflection happened at x equals 2. 6x minus 12. All right. So what have I forgotten to say at this point? Not too much, other than I guess I started talking about concavity here. All right. Because when x was -2 and you cubed, you're kind of going up at average rate from one spot to the next at 7 to 1, then at 1 to 1, then it was 0, then it was 7. Yeah, looks like the slopes are decreasing. They're still positive, still going up, but decreasing and then increasing again. I guess that's what we're talking about. We're talking about point of inflection. And that came from, well, I know how to graph 6x minus 12. Looks like 2 is really important. Seems like there's a negative and a positive y value and a sign change there. And seems like the negative kind of match up with that interval of concave down, and the positive seems to match up with that interval concave up. Something to think about. All right, so that's half the story. So I gotta, do this another video at some point. I just don't think it's quite yet, because there's a whole nother side to this. I mean, we've been just doing a process. No different than on the test when I ask you, all right, I'll just do a random one, 3 plus or minus 7i. Well, that comes from x squared minus 6x, 9 and 49, 58. That came from completing the square process. And if you can complete the square to get the answers, you should be able to do the inverse operations to get back to what you started with. A to B, B to A. It's what we do all the time in a class. So what happened if I kept putting layers and layers of volume on the box? What happens to the volume as I keep putting another layer and layer? And each of these layers, by the way, is what we call a derivative. Yeah, putting a lot of thoughts in your head. All right, well, that's the inverse operation. That's the inverse operation of multiplying and dropping down one. It's kind of what we did here, right? I mean, we went from x squared, a two-dimensional process, to a one-dimensional rate of change. So it went down a dimension. So if I multiplied and dropped down a dimension, multiplied and subtracted a dimension, then what's the other direction? Well, adding. Instead of dropping down one, we add one. Instead of multiplying, we divide by our new number. So let's do that. This is x to the 1. Let's add 1 to it. Let's go up 1. And then divide by that. I'll write 1 plus 1. You tell me what you think. I think you get that. And what if we did minus 12x? We go up 1. Make it a square. And then we divide by that number. Where am I? Oh, I should have done this one. Sorry. Lost track of where I was going. So this is actually x to the 0. If I go up 1 and divide by that, well, there's that. All right, so it kind of brings me back to almost all of what I started with. And then I suppose, just like completing the square, I know a 0 gets me minus 10, right? So a 0 gets me minus 10. And right now, if I do this, I get 3x squared, minus 12x. If I put 0 in now, I get 0. But if a 0 gets me minus 10, and I know that, nothing's stopping me from writing minus 10. Okay, so that's the other half of the story. And it's interesting that I know a couple of things. I know f of 2 gets me minus 22. Okay. And f prime of 2 gets me 0. That's interesting. And I know that f of 5 gets me 5 up here, 75 minus 60 minus 10. So I just kind of looked at 6x minus 12, and I can see that from 2 to 5 is 3 units of width change. And if I put 5 into this function, I get 18, 5, 30, I get 18 units of height. 3 times 8 is 54. That's a triangle, so that's 27. Oh, interesting. Interesting. Working with that seems to get me the change. Negative 22 to 5. 27. Wow. Wow, that's interesting. Yeah, and I guess it's feels like there's some sort of connection here when I fill in that area. When I change that area, changing that area, of course, isn't the cubic. Changing that area is over, down. Another one, just the front. Over, down. And that's accumulating area. Okay, I just made that dimension a little bigger and that dimension a little bigger, and the area got a little bigger. Well, magic box is going away. All right, at this stage, the brain is probably overwhelmed if you're a just beginning student in Algebra 1 or Algebra 2. or pre-cal, probably not talking about these things at all. And I think you should. I think you should be pointed towards what's the next level of study. The next level of study is based on all the foundational stuff you're doing now. So if you're going to have success, if you're one of those few who wants to head towards engineering and architecture and all those other things, you have to get some conceptual awareness as to where this stuff comes from. I think, what the heck am I? I'm just somebody who's taught this for a while, right? But that gives me some experience and some opinions. And it is this old man's opinion that the more you talk about the concepts, the more pictures you have in your head as to what's going on, the stronger your understanding of these processes. Because a lot of students, drop right out after pre-cal and cal because they're like, well, what am I looking at? I don't know. And even some students will go beyond if you really kind of ask a couple of simple questions like what's a radian, what's a logarithm, things like that. A lot of times it's memorized forms for a test. And I don't think that's necessarily what we're after here when we're talking about getting a good education. All right. So I think you should try to dive in more deeply, look more closely, be more mindful of the calculations that you're looking at, and it'll serve you well as you go forward. All right. I'm kind of right in the sun, who knows, but hopefully there's some fodder there to move the needle forward. All right. And I'm talked to Yasser or heard from Yasser in a long time, but I know there's been trouble overseas and I hope he's safe and sound. All right. Bye-bye. Oh, don't tell me let's try this again. There we go. Okay. End the meeting for all.